Good. Yeah. So previous time we talked about what is the definition of connectivity and all sort of graphs, and we reach to the definition of trees. So today we are talking about trees, and also hopefully time permitting, we talk about also binary search trees, which are the way that STL in C++ has implemented a map there. Unordered map was the hash function that we talked, but map actually was implemented through binary search trees. So we will talk about them. Good. So what is a tree? So a tree is a particular graph So a tree is a connected graph that does not have a cycle. So yes, so it is a connected, undirected graph with no cycle. So two properties: one, connectivity, and then two, no cycle. So if this is for undirected graph, for general graphs, if it is a directed graph and there is no cycle, it is called DAGs. We talk more about them. So this is called a DAG essentially. But DAGs, in some sense, they can have a cycle. Okay, so DAGs, they don't have, they call directed acyclic graph, means that they don't have any directed cycle. How they can have actually some kind of undirected cycle. This is undirected cycle, but there is no directed cycle. There is no cycle like this essentially. These are called directed acyclic graph, DAGs. But this is for directed. But here, we mainly talk about the one that we are using the most would be the undirected one, the tree one here. So it is a connected graph with no cycle. Actually, there are three properties, which are all of them are equivalent. So a tree is a connected acyclic graph, or the third condition is this one. So a tree, let me just write, is an undirected graph with 2 out of 3 conditions above. So a tree is an undirected graph with 2 out of 3 conditions. What are the 3 conditions? One, it should be connected. 2, it should be no, it would be 2 is no cycle, and the third, that the number of edges is the number of vertices minus 1. In 2 of, so this is essentially this is the properties of the trees, and these are some equivalent theorems. I will prove some of them here, such that you have some ideas about them. In 2 of these conditions that you will get, it implies the third one. That's essentially the idea. So a tree is is essentially. So I think I will say that any 2 implies the third one. So here we know that any 2 of them implies the 3. So if the graph is connected and has, say, no cycle, then it means that the number of edges should be number of vertices minus 1. Or if the graph is connected and the number of edges is equal to v minus 1, then it means that it should have no cycle. Or if it does not have no cycle and the number of edges is e equal to number of vertices minus 1, then this graph is connected. So that's the interesting thing about the trees. And let me prove, some of them. This is actually some good exercise for you to prove all of them. So I don't prove all of them. I just give some ideas about it. Lots of them actually you can prove by induction. But let's, for example, prove this one. If G is a tree, then, what's the meaning of a tree? So tree by this definition. So if the graph is connected and no cycle, and this is the third one. So if the graph G is a tree, so it means that if it has 1 and 2, then you want to say it has also 3. Good. So why is it the case? So, so we need to actually prove this one. So how do we prove it? So consider a tree. Good. So start from one vertex, V. Then go to the, any adjacent vertex here. So from V, you may go to W. Then from W, find any adjacent vertex that, other than the one that you came there, maybe to this guy. So this graph is connected. And there is no cycle. It means that you cannot come back to any vertex that you have seen before. So this cannot happen because there is no cycle. It means that if you start from this process, essentially start from one vertex, and you go one by one, at some point you should reach to a vertex that you cannot go out of it. Good. What would be the degree of this vertex? The degree of this vertex, because you just came there, the degree of this vertex is 1. But the degree of V is equal to 1. In some sense, V is a leaf here. So what can we do? Then we are using induction. You see, we cannot say that we are considering a tree of size n-1, and then we create a tree of n, because there are lots of ways that we can do it. But we are getting a tree of this is the lemma that I say, that essentially that there is always a degree, the vertex of degree 1 if the graph is tree, means namely if it is connected and no cycle, because you can start from one vertex, you will go there until, and you know that you cannot come back to the previous vertex because there is no cycle. So it means that you should end at some point, and that vertex should have a degree 1, because you will come there, but you cannot go out. So the degree of this vertex should be 1. So what do we do then? So then you consider this V. So this is the part that so this is the lemma that I have mentioned. There is a vertex of degree 1. So I say this vertex is V. Then what do? I will delete V and one edge that is attached to that. Now, the rest of the graph that I have it has n-1 vertices. And it is a tree. Why? Because there is no cycle. I didn't add any cycle. And this vertex is only connected to this guy. So it means that the rest of the graph should be connected to each other, because this guy is only connected to this guy. So it means that everything else should be connected to this vertex, because it was a connected graph before. So we have a tree of n- vertices. So it means that now I'm using induction hypothesis. So induction hypothesis says that this tree should, the number of edges should be n-2. So this is the number of edges. Size of E. So this is the size of V is equal to n-1. And again, note that how do we go from n to n-1? We cannot go from like n-1 to n, because we don't know what edge we should add it. So first we show that there is a vertex of degree 1. We deleted that vertex and the edge attached to that. Then we say that, okay, this guy has one less vertex, and it still is a tree, because we don't have any new, we didn't introduce any new cycle, and the graph should be connected, because the whole graph was connected. This guy is connected only to this guy. It means that everything else should be connected to this guy as well. So this graph is connected, has n-1 vertices. By induction hypothesis, should have n-2 edges. Now, this new graph had only one vertex more and one vertex, one vertex more and one edge more. So the number of the original graph, it was V, the number of here, the E should be n-1 because there's one more edge that is there. So that proves this thing. So that says essentially that 1 and 2 imply 3. Clear? Great. I can give actually maybe one more example of this. There are essentially, you need to say that any 2 implies the 3, and this is an exercise for you to prove it actually there. I may give one more example that if the graph is connected and has no and the number of vertices is equal to number of so the so actually lots of them you can prove it by induction. So this is the okay, let me prove this one. So this might be better. So let's the other one you can prove it. I mean, you can think about it. That is a good exercise, and it is also in the UDI members book. You can search for it, and of course on the web. So here it said that if the graph is if has no cycle, it means that if we have 2, and also the number of things, the number of edges is 3, then 2 and 3 implies the graph should be connected. Good. So why do we have this one? And why, if the graph has no cycle and the number of edges is v-1, then the graph should be connected. Again, we are using induction. First, we know that like here we have the E is equal to v-1. We know that the sum of the degrees is equal to the sum of the degrees of this graph is equal to 2 times number of edges. Good. What's the meaning of that? It means that we cannot have that all vertices have more than one. Essentially, so what's the meaning of that? These 2 together says that there is a vertex of degree 1. Actually, there are 2 vertices of degree 1, but 1 is enough for us. Because the number of, so if the degree of each vertex is at least 2, then we can show that actually then you have at least 2v. You have at least 2v, the sum of the degrees would be 2v, and it means that the number of edges should be at least v, the size of v. But we know that the size of actually the number of edges is v-1. So it means that there should be at least 1 vertex of degree 1. Actually, there are 2 vertex of degree 1. So then we are doing exactly the same thing that we have done it before. So we know that there is a 1 vertex of degree 1. So this is v. Again, remove v and the vertex which is attached to that. Now, in the remaining graph, it has no cycle. So still we have 2 because we didn't introduce any cycles. Now, we have removed 1 edge and 1 vertex. So it means that for this new graph, also the number of E prime is equal to V prime minus 1. So it means that for this graph, that the remaining graph, the number of edges is equal to number of vertices minus 1. And it has 1 less vertex. So here, so we have this property 3 and 2. Now, by induction hypothesis, we know that from this one, by induction hypothesis, again, the basis of induction, you can check if you have only one vertex is always correct. And so 2 and 3 implies 1. So it means that the whole graph here is connected. Now, if the whole graph is connected, you will, so it means that everyone is connected to this vertex, and this vertex was connected to this. So it means that the whole graph is connected. Again, we are going from vertex of degree n to vertex of degree n minus 1. We create an n minus 1. So the proof for this one is also very similar. So that 1 and 3 implies 2. It is exactly the same thing. So because E is equal to V minus 1, we know that there is a one vertex of degree 1. And so we can just remove that vertex of degree 1. And then we know that the rest of the graph should be still connected because this guy was just connected to this one. And the number of edges is V minus 1. So by induction here, 1 and 3 is implying 2. So there is no cycle here. And this one also, we have no cycle because this vertex is only attached to this one. The degree of this vertex is 1. So the whole graph has no cycle. So this is essentially the proof that all of these three things are equivalent. The graph is connected. So any two of them implies the third one. A tree is a graph which is connected, no cycle, and the number of edges is equal to number of vertices minus 1. And again, any two of them implies the third one. You don't need to say all three. Any two implies the third. Is it clear so far? Please unmute and answer.
Yes.
Good. And the proofs are... Yeah, go ahead.
So when you remove the vertex and the edge, how is the number of edges still V minus 1? Isn't it?
No. You see, we are deleting. So we knew before the number of edges is equal to number of vertices minus 1. Correct? I remove one vertex and one edge from this graph. So still we have this condition satisfied in the graph which has one less vertex. The number of edges went down, but the number of vertices went down as well by 1.
Oh, okay.
So essentially, we say that we have the graph which has one less vertex and one less edge. And this graph, we knew that by induction hypothesis, it should be correct. And again, all of them, the base case is just one vertex. If one vertex, of course, in this case, this is a connected graph. There is no cycle. And the number of edges is 0, which is number of vertices 1 minus 1. So all of them is correct for one vertex. That's the basis of the induction. So these two are very similar, this one and this one. This was a bit different because there you need to find a vertex of, again, I mean, in some sense, in all of them, you're finding a vertex of degree 1, but it is a bit different in this two, and this one was a bit different the way. So here we are doing some path, and then we said that we should stop somewhere. Here we are using the fact that the sum of the degrees is twice the number of edges, and we say that not all vertices can have degree at least 2. So 2 of them should be 1. And again, for example, there should be no vertex of degree 0, because if the degree 0, for example, here we have essentially the connectivity things will be violated. So this guy should be connected to the previous vertex. Good. So that's the proof that, I mean, so for the case of 0 is easy essentially to handle if the degree of this vertex is 0. That's this one. So so these are the main properties. So trees are very good, and these are very good data structures as well. That's the thing that we are using them a lot. Good. So let's talk a rooted tree. So generally, when we have a tree, I mean, the trees are represented something like this. We put one vertex on the top, and then we are putting all other vertices below that. This is generally, essentially, a tree we are representing here. So in that case, this guy and the top guy is rooted. And here, we can have a directed tree or rooted tree. So all edges can be like this, that are going out of the root, or it might be the reverse. Sometimes the people consider, so in this case, this is a single source. This is a source for everything, and it can be single sink. everyone comes back to this. But in a way, I mean, we don't need to also put all of these directions. When you put, I mean, at least when we draw it. When we draw it, there is one guy which is the root. And everyone below that, you can think about that root has an edge to them, or they have a edge to root, and so on. Now, when we have this thing, I mean, when we have this rooted case, that one vertex is the root, generally is the top, these are something that we want to say. So in that case, this top guy essentially is the root. Then this, if one vertex is above this guy, this is called the parent. So this is the parent, and this is a child. So this is a child, and this is a parent. So this vertex is like that. So if one vertex is just below that, is called a child. If one vertex, say for example, if this guy is like in more than one things, it is called like more than one level down. It is called so this guy calls ancestor. This guy which is below is descendant. So if it is just, so ancestor and descendant would be essentially the same as parent and the child if that guy is just connected directly to the other. These rooted trees are very good because generally also they can represent hierarchical structure. So you may consider this is the root, and has several children. So if you can, sometimes a hierarchy, for example, it is called hierarchical clustering. So you may consider the whole graph and say each vertex should be its own clusters. And then maybe these two vertices, they form another cluster. And maybe these two guys together, they form another cluster, and all of them form another cluster. So these are this kind of, the trees are very good to represent hierarchical structures as well. And also these are very good for data structures. So this is the, also we need to so here, oh, by the way, these guys that they don't have any children, these are called the leaves. So these are called the leaves. This guy is called the root, and this other guys, it is called inside vertices essentially. So the vertex which is not a leaf and not a root is inside vertex. A root is also inside vertex. So any questions so far? Good. So you can, if you have some kind of tree like this, I mean, you can consider this guy as the level 0. Yeah, so the root is called level 0. This is the level 1. Then this is level 2. Level 3, and so on and so forth. So this is, and the maximum level is called essentially the, it is called the height of the tree. So what is height of tree? Is the maximum level that we have it. So this is another way you can consider, you can define the depth of a node. So depth of a node is the number of is the length of the path from the root to this guy. So for example, depth of the root So in some sense, depth and level you can think about. Sometimes, I mean, depth and level, they will consider it differently. They define sometimes the distance. The different papers are different, essentially. Sometimes they define, for example, the level from the leaves. So the leaves are level 0 and so on and so forth. But this is more common. Level 0 essentially means the root. Level 1 is the next vertices that root connects to them, and so on and so forth. And the depth of a vertex is the, I mean, the depth of a vertex, again, here you can define it from the root, or you can define it sometimes from the leaf. But generally, again, the depth is the length of the path. And note that from each vertex to each vertex, there is a unique path. So there is a unique path between any two vertices in a tree. So I will say that the unique path to vertices of the. So any consider there's a unique path. So if you consider this root to here, there's a unique path. So the length of this one, the number of edges here, the length is the length of the path is the number of edges. It can consider the depth. So in that case, depth and level would be the same. And the maximum depth is called the height of the tree. So maximum depth, or like in this case, level, because these are the same. The maximum depth is a height. So for example, what is the height of this tree that I draw here? Please unmute and answer.
3.
Yeah, it is 3 because this depth of this guy or the level of this one would be 3. So this one has a height 3. Also, one thing it is important. So like here, when we are considering the tree like this, so each vertex that you are considering it has in degree 1. So in degree in a directed graph is means that the number of edges that are incoming to this vertex. So for any vertex except the root, the in degree is 0. There is nothing is coming to the root. But anything else, the in degree is equal to 0. So is equal to 1. Odd degree is the number of children. So this is odd degree. So in degree essentially is the edges, the vertices that are coming to a number of vertices that are coming to a vertex, and out degree is the one that are going out. So this is generally for any directed graph you can define it. In degree versus out degree. So then what is a binary tree? So a binary tree so we have a saying. So a binary tree is the one that all degrees, as I mentioned, the in degrees of every vertex is at most 1 in a tree. For the root is 0, and for everyone else is 1, because there is from one vertex that are coming. The odd degree is less than or equal to 2 is called binary tree. So what is a binary tree? A binary tree is the one that the odd degree is at most 2. And in this case, if it is a binary tree, because we can draw it, we can say this guy is the left child, and this is the left child, and this is the right child. So how can we actually have a represent a tree, or say in binary tree especially? So, for example, in C++, if you want to use SDL, I mean, that is, so these can be just one pointer. So each vertex, you can think about it, has one parent. I mean, it can have a pointer to the parent as well. So you can, so each vertex, you can consider it has like this is the vertex. I mean, if you want, this is the vertex V, for example. For that, we have 3 pointers. So, so this is the vertex V here. And here, it has, so it has, one of them will actually go to the parent, if you want to have a parent. The other one goes to its child, it goes to its 2 children. I mean, it can be, one of them can be none. But if it has a left or right, it can go to this guy. So a binary tree can be represented like that. Even if there is no need to be a binary tree. You can think about, instead of this one, this can be a vector, or it can be a list, essentially. So if the degree is greater than 1, that is still fine. So in general, each vertex has, I mean, it might have more than 1. The in degree can be even more than 2. But no difference here. So you can think about it that you have one, essentially, you have one pointer to the parent generally. That is good, because if you want to go your parent, it is easier. So in some sense, this is the difference between the linked list and doubly linked list. So in doubly linked list, I mean, each vertex or each element is also connected to the previous guy. In the list, you are just going to the forward guy. Generally, it just adds a constant overhead, but for some problem, it might be much easier. For example, if you want to find the parent, if we have the directed, I mean, essentially this to the parent, that would be very easy to do that. Otherwise, we need to go through all vertices and see for which vertex this guy is a child of that. But anyhow, so that's a way. So having to, so one thing, essentially, this is for parents. And all these guys are for children. And the children, I mean, it can be, as I mentioned, it can be more than 1. Maybe this is like the 3rd guy is going there and 4th guy and so on. So this is just some kind of, you can consider, this is just a list that you have it. And each list essentially goes there. So this is exactly the same thing in Python. You don't have, I mean, the pointer, but then essentially you can define a class. And you will say that I have left and right also. So you can define a class of B3, means binary tree, and you will say left and right also are B3s. Essentially means that, so each class has 2 elements, left and right, and each of them is actually a B3. And when you create an element, so you can consider for a vertex that does not have any, I mean, for example, this one, if you consider this vertex that has, so this vertex, it is a leaf. For this guy, actually, the children would be null or nil. So you can say null or nil, essentially, on any of these languages. So null or nil would be the children. But if, so in Python, you don't have pointers. You just say that my children are the same, essentially, class as me. At C++, you have a pointer. You can still say that it is a class, but it will be more efficient to just say the pointer. Good. So that's essentially, we can have a linked list, as I mentioned, for children and parents. So this is the way that you can represent trees in each of these cases. One to the parent and a list of children. That's a typical way that you can do it. So, and we are talking about this. Let me see, is there anything else that I want to? Yeah, as I mentioned, so you can, I mean, you can say nil or null. These are some of the ways that I have mentioned it. I mean, these are the, so this is the one that I have mentioned. This is for each node, you have a parent and you have the children, essentially. There is this way that also, I mean, you can also represent it. This one, less people are using it. You can say, if you want to just have, so if you have not a binary tree, and you want to have still not a linked list to be used, you can say this one. You can always have 2 pointers. Each vertex, you will have it. It has 2 pointers, one to the parent. The other one is for the rightmost, actually 3 things. So you have it to 3 things essentially. One to the parent, one to your first child, and the other one is to your sibling. This is also enough to do that. So you have one essentially pointer to your parent, one to your first child, and the other one, this B is called sibling. Sibling means the children of the root. So you have it to the next sibling. This is tree. Also, you can actually represent not necessarily binary tree, a tree that can have any odd degrees, but that would be somehow less efficient. I mean, if you want to find the, yeah, you can still, do almost all operations with this one, but this might be easier to implement if you want to just use it in C++ or Python by just using the list for that. And anyhow, lots of cases that we are considering are the cases that the number of children are limited. Maybe it's not binary, maybe it's ternary, but there are 3 children. So in that case, that should be fine to keep the level of all children. So here, the main issue here is that for the children, we cannot have all of them. So we are just keeping a link to the first child here. And then we need to, in addition, we need to also keep track of the sibling, because for the parent, for this parent R, if you want to find all his children, we need to go to the first child and take the next sibling, next sibling, next sibling, such that we can find the children of this guy. Anyhow, so that's about trees, and this is the way that we can represent them either in C++ or in Python. Now let's go and talk about binary trees. So binary trees. So there are some heaps that we can also. These are also some kind of binary trees that we talk about their implicit representation later. But as we mentioned, so you can consider for binary tree, and we are assuming that this is essentially a plus a node. You can consider a BT node. This BT node has some value in it. This is the value of the node. And then we have the R child, which is itself a BT node. This is in Python if you want to do that. And then left child, which is still a BT node. In C++, both of them would be essentially somehow the address of this one. These all would be pointer. That's in C++, but in Python, you don't need this, guys. Good. So this is the general thing. The BT node, the binary tree node, has some value. It has a left child and the right child. These are the things that we can do it. And this is the binary tree. This binary tree is the way that, as I mentioned, the maps in STL, in C++, it is implemented there. We talk about hashing, and we mentioned the unordered map is actually are implemented using hashing. The running time of the operations essentially in hashing is generally order 1, but these are random ones. And in the worst case, it can be very bad. It can be order n. But the maps, they are guaranteed that these are actually log n. In that sense, actually, one good thing about the binary search trees, these are the ones that exactly they are these dictionary operations are supported by maps in STL or in generally binary search trees. So, and these are also these unordered maps. So as I mentioned, so unordered map. This unordered map actually are just hashing. And these are unordered map in str. So here we are talking about the dictionary operation. And again, the way that we are implementing them is using this BT node. This is a class, you can define it. This is a class of this kind, the value, rchild, and refchild. So in C++, we have unordered map, which are hashing, and the ordered map, or just map, essentially, which are, they are implemented using C++, using this binary search trees. And both of them, they are supporting this dictionary operations. What are the dictionary operations? These are three things: search X. So it says that whether X, find X, whether essentially you will find X, and or you report that X is not there. X in some sense is the key. So for example, you are doing, I don't know, you will say you are defining a map, and then you will say this map, for example, map of, say map is define essentially M as a map, and then you will say f of, I don't know, A, B, C, D. So here, this is the key. This is X that we are talking here. So map of X is equal to something. So here, this you can consider the BT node. They have not only value, they have also a key as well. Sometimes value and key are the same, sometimes it can be different. So here, when you have a mapping, so this mapping, I mean, this, as I mentioned, in general, in the C++, you can consider a whole graph, a whole class, an object of a class, and map it to something. How can we do that? You can think about this, all objects are essentially are JSON. JSON, you can turn them into strings. So anything at the end is a string. So you can think about all these keys at the end is a string, essentially. So you only need to define a map of a string. That's the most general form in some sense. And then map of this string is equal to trees, say, for example. It means that there is a key here, and so the key is A, B, C, D, and the value in this case would be 3. Again, sometimes value and the key are the same, sometimes not. But a mapping is the one that we are doing that, and here this key is X. So whether we are, or like essentially in the dictionary operations, we are doing that. Find X essentially determines whether X is in there or not. For example, if it's a dictionary and you are searching a number and it is not there, then it gives an error in Python. So you need to be careful. If you are using a regular dictionary. There are some others that they don't give error. So that's search X. There is insert X. What is insert X? It is if defined, if it is already in there, it does not do anything. Or if it is not there, then it is inserted. Or delete X, that if X is not there, then essentially if X is not there, then it does not do anything, otherwise delete X. And again, so here, for example, you can have this one, insert X, a new value. So in that case, it finds X and then change the value. So it is essentially, it means that f of this is equal to 4, for example. It is already is equal to 3. Then you make it 4. First, it finds the key and then puts the value equal to 4 in this case. Any questions? Please unmute and ask questions, if there is anyone.
Like, usually is hashing used for dictionary operation?
Sorry, can you repeat?
And usually is hashing more used for dictionary operations? Or
I mean, it depends. I mean, if it is, for example, as I mentioned, you have the unordered map and ordered map, unordered map and just map in C++. It depends to your case. So hash in general is a randomized algorithm. As I mentioned, if there is too much insert and delete in a hash, it can actually make it less efficient, as we discussed, for example. It depends what type of hash function you have implemented it. Either there is a collision possibilities, or it would be the case that, I mean, in the worst case, it can be very bad. Binary search tree, I mean, as we discussed, and it's like a little bit generalization, it is AVL trees. That has these good properties that, I mean, you can say that the worst case is log n. So hashes, lots of operations are order one. So for hash, lots of operations are order one, but this is randomized, and this is somehow the expected time is order one. But for binary search trees, lots of them actually is order like. Again, the binary search tree itself can be order n, but there is some slight variations called AVL tree. Is like n. So it depends. You should check essentially. For example, I mentioned some of this, but like if you want to see the exact things, so Python you need to check. I don't remember on top of my mind that the dictionary is operated like done via hashing or via binary search trees. But depending on which one, and if you know that it is mentioned that lots of them are open source, so you can see that. And depending on which one it is used, then for your different application, you can use it essentially. In general, if the hashing you are doing lots of insertion and deletion, it can be an issue. For binary search tree, there's no difference, always a log n, but then it might be a little bit log n more than order one in terms of running time. It's not much difference though. It's already is a good thing. Good. Now, what is the property of like this binary trees? So, as I mentioned, for binary trees, we can have key left and right. You can have some valuation as well. So, but the main thing is this key. The key is very important. So, what are the properties that we have? Each key. So, consider each node here in the binary search tree. This is the important property of that. The key here. So all keys here are less than or equal to this. And all keys here, these are all greater than or equal to, sorry. So all keys here are less than this key, and all keys here are greater than this key. This is the main property of binary search trees. So this is the left child, and this is the right child. All things in the left, not only the left child, but all of these descendants in the left are less than or equal to the key here, and all descendants on the right are greater than or equal to the key here. Okay. So that's a property. And any binary tree, any binary search tree that has this property for any key, so that's the thing that we say that it is consistent if it satisfies this property. For all nodes, we should satisfy this property, not only for the root. For every node, we should have this property. And in this case, it's the case that we say that this tree is a consistent tree, is a consistent binary tree. Now, let's see the operations that we can do it in this. So how can we do a search operation? So you want to find the keys. So you want to search X. Again, search X, essentially, it means that you want to put, say, a map of X to something. You need to find, to do this, do anything like map of X, you need to find search X. So how can we do that? So this is X, so you consider the root. And then you will compare the key of the root and this X. So this is the root.key versus X. So you compare it. If X is greater than, if X is equal to root K, then you are done. If X is greater than root K, it means that X you should come to this essentially right child and do this one recursively. If X is less than key, then it means that you should come to the left one. So this is the left child, and then you will do this one recursively on the left or right. So if either it is equal, you are done. If it is greater than that, you will go to the right. And if it is less than that, you are going to the left. Is this clear, the search operation?
Yes.
Good. So that's, easy one, essentially. Now, what about the insert operation? So the insert operation, so for insert, again, you can consider, say, map of X is equal to 10 or some value. Then, it is exactly like search. So map is exactly, so insert is same as search. So there are two cases that happen. Either when you try to insert an element, you will find that element. So in that case, because so what is the properties of keys? Like, for example, in the dictionaries, keys are unique. So we are assuming that there is some uniqueness between the keys. You don't need to have it so binary search tree can happen if the keys are not unique. But generally, for the dictionary operation, we are assuming there is a key and this key is unique. So when you search for the element, either this key is there, this X is there, or not. So if not, say, for example, here, you are coming here. So this is the one that I'm doing. So you are, let me just draw it here, actually. So here, this is the X. You are comparing it with this guy, then you are comparing it with this guy. If it is equal, then you are done. Then you are comparing it with this guy. So when you come here, then you didn't find it. And this is a leaf. Then what do you do when it is a leaf? So if X, you came here and X is not equal to the key of this leaf, then depending whether X is larger than this guy, you may so if X is larger than this guy, then you are inserting it X here. And if it is smaller than this guy, they are doing as a left child of this. So that's a very simple one. So insert and search are essentially the same. So if either you find it, if not, if you don't find it, then you are at the leaf. And then you are inserting it in the left or right, depending whether X is greater than the key of the leaf or less than the key of.
I have a question. If X is in the tree, do you update the value or?
Yeah, for example, here we are just assigning they are inserting X. You can consider you insert and delete it. But yeah, if you want to change the value, if you say map of this is equal to some number, yes, you are just changing the value of that. Because here we are assuming the keys are. But you can always consider change of the value equivalent of insert. First delete the guy and then insert. It might be less efficient, but that's an abstract way of thinking about it. So in some sense, this search, insert, and delete are the main basic operations. With that, you can change the value. Whenever you want to change the value, delete that key and then insert it again. It's a new value. Good. So now let's go to the next one, which is a bit more involved. So the one that is more involved is the delete operation. So you want to say delete X. Good. So you have again this tree. And you have X here. So this is X, you are coming here, maybe you will come here to here, you are comparing it. No, good. So if this X, it happens to be so even if you don't find this X, then you are fine. Say, okay, there is nothing to delete. If X happens to be a leaf, then what do? You just delete it. So to delete this guy, you will just, essentially, if you have used some memory, you can just essentially remove the memory of this one, or essentially make the memory free. And then for this guy X, the parent of this guy, you just say that this should be null or nil or any of these things. So then that's easy. And again, this one, as I mentioned, in each of these guys, they have a pointer to the parent. So when you find this guy, you can always go to the parent and just from the parent, delete this guy. So that is easy. The problem becomes, then the issue becomes more problematic when actually X is here. So you are finding this X is here. See. Yes. So X is here. Good. So let me just. So if X is here, then what will happen? So and this is the tree. So the issue is that in this case, what can I do? So how can I delete X? Any ideas? The issue is that when you delete X, then the structure of this binary tree essentially may collapse because it's not easy to replace. So we cannot easily. So one way is to, okay, maybe replace this guy with one of his children. But the children may have already 2 children here, and then you make it a ternary tree. So you don't want that this happens. So what can we do? Say here it is something like this.
Would you swap it with like maybe with the leftmost leaf node?
Yeah, good. So actually the way that you can do it is this one. You have 2 options. If you want to delete this X, you cannot delete anything here. So what can you do? So you can come to the right child. So you know that this X is less than everything here. So if X is less than or equal to everything, or less than everything if all the keys are unique. So you want to find who should be the correct guy. The issue is that who is after X? To see who is the smallest guy in the whole subtree, you need to do that. You will come to here, the child might be not the correct one. So what can you do? You will come to the, say, for example, here, the right child. And then you will go the left. Then when you go to the right child, then you will go all the way left. So you will take one R and then lots of left until you will find essentially a leaf. Good. It actually, you can see that the leaf guy here, when you go left all the way, this guy is the essentially the least element in the whole tree. And we know that this least element is greater than X or greater than or equal to X. So that's actually a good appropriate guy to replace X. So, and this guy would be a leaf, or say, I mean, this guy may have actually one child, but if it has one child, there is no problem because you can just delete this guy, replace this. So if the guy has only one child, essentially, so if you find X and X has only one child or zero child, that is easy. If zero child, I mean, then you just delete it. If it is one child, then you will just replace X with his child. That is fine. So you just replace X with his children. This is one child and we are fine. So find this guy, this is the X, then you will find this guy, you will delete this guy. And then you will insert it instead of X. So you don't change essentially anything. So this guy that you have deleted here, you just bring it here with its key value, etc. So you will delete X and instead of this guy, say this guy is X prime. So in this case, you will delete X and instead you will put X prime. Is it clear?
Can you take the rightmost leaf node from the left subtree?
Exactly. So that's the same thing that I have mentioned. So you have done the same thing. You could do actually these operations as well. You could come to the left and then go all the way right. That is totally the same thing. You can do either of them. Either of them is fine. So this guy is the largest guy in this tree. It can still, and it is less than or equal to X, so it can replace X. Okay, so these are the three main operations: delete, insert, and search. However, the same thing, now the things that we are seeing here is that, as you can see, all of these operations, what is the order, how much running time or how much comparison that they take? The comparison, I mean, then you can actually see that the running time of this algorithm would be the height of T. If you have, this is the 3T, the height of this tree would be height of T. Now, if this is, of course, if you have, this is something that is called balanced binary tree. If it is something like this, you can say the height of this guy. So if there are n vertices here, the height of this 3T would be equal to log n. N is the number of vertices, which is good. So everything that we have, because for search, insert and delete, we are just going the height of, I mean, we are going through one path, essentially say depth of this node, and the depth of this node is at most height. So it would be order log n. However, you can see that if these elements that you are inserting are in a random order, so they are coming in a random things. This is the same thing that we were discussing for quicksort. For quicksort, we knew that if your elements in the array are essentially in a random order, or these are coming from some distributions, they are coming in a random order. Somehow, if they are random, then we knew that for this case, the running time of the algorithm was essentially log n, even if you choose the first element as a pivot. So the same thing here. We know that if the like here, I need to go down. Yeah, so that's the thing that I mentioned. So you know that if the keys are inserted in a random order, so if you have a key, if you have some of these keys that you want to put in, you just randomly permute it and then insert it there, then we know that in that case, the expected height of this tree is log n, and it is very similar to the quicksort. However, if these are the ones that are sorted, so if this is the case that, so this is first you are seeing that this one, so you are, so the elements that you have that you want to choose, that you want to insert is 1, 2, 3, 4, 5 to n. So in that case, if you insert it, the first guy is coming here, 1. Then the second guy is coming here, is 2. If you are, then the sixth guy is coming this here, is 3. And finally is n. So in that case, the height of this tree, T prime, is equal to actually n, or n minus 2. So in that case, actually, so this insert, so if they are coming in an ordered way, if you insert them, actually some bad things can happen. So in that case, the depth of this tree, or like the height of this tree, can be ordered n, and this would be very inefficient. So to resolve this, we need to use, so this, to prevent this worst case, we can use AVL trees. AVL trees are a special, case of binary trees. But when you're doing essentially insertion and deletion, you are doing it in a way that you make sure that the depth of this tree is always ordered like n. In this way, you have a guarantee that the depth of this guy would be at most like n. We will talk more about AVL trees next time. So we will talk about AVL trees, and which are the generalization of binary trees, and heap sort, which is another way of using trees essentially, or heaps, which are another way of using trees, next time. And then I think we are done with the heaps. We will talk more about graph algorithms, and then time permitting, I will put some videos for you as well for the this MP hardness as well, if there is not much time at the end of the class. Good. Any question?